if you can see this diagram, we used it yesterday, giving us the principal quantum numbers 1, 2, 3, 4, also named as K, L, M, N, and we talked about the magnetic. I think that these people are joining late. I will just stop and meeting them. You should learn to use your corporate mail to join without interrupting the others. So let's look at the shapes. These are the shapes, like the 1s orbital. It looks like it's spherical, a bit compact when you compare it with the 2s orbital. And when you go to the other orbitals, you get different shapes. The p orbital, we can have what we call as px, py, pz. And this px, it is aligned to the x-axis. The py is aligned to the y-axis. The pz is aligned to the z-axis. That is what we talked about, aligning of the orbit, the shape and the way they are aligned. Now, when we come to D, we can have D aligned to X and Y. That's why we have here X. Let me just zoom it out a bit so that you can see. You see here, and this is D, X, Y. So the alignment is along the Z, the X and the Y axis. So it is in the horizontal plane. Now this one is in the Z plane, and you can see the others, and like this one. So we have the Ds having different shapes and different orientations. This is what I did mention. It was not easy for me to draw in on the board. Is interrupting the class when you join late. So remember this, which we mentioned about the angular quantum number represented by L. I think that there was other diagrams we wanted to see. Oh goodness. We wanted to see these diagrams also. See this. Okay, not this one. The crystal structures we talked about, we said we have amorphous, polycrystalline, and single crystal. You can see amorphous, there's no order in the way the atoms are arranged. And polycrystalline, there is some order to some degree, and that order changes. But for crystal, single crystal structure, we have order throughout the volume and in 3 dimension. Then now we did talk about the unit cell, and this is a good diagram to represent the unit cell. You can see the angles marked alpha, beta, and gamma, and also the unit cell, the unit vector A, B, and C. Now the A is aligned, is the unit vector on the x-axis, B the unit vector on the y-axis, and these angles can be any value ranging from 90 degrees to more than 90 degrees or even less than 90 degrees. And the common structures which we have, we mentioned the ones which we could draw easily on the board. The symbol cubic, where we have the atom sitting at the corners of the cube, and what we call the body-centered cubic, where an atom sits in the center of the cube. So we call it BCC, or body-centered cubic. The FCC, or face-centered cubic, we have atoms sitting at the faces, as much they are also atoms on the corner of the cube. Then another structure, we said there are several. Another structure is tetragonal, where we have, it is not cubic, but for this face, A and B are equal, but C, which is this longer one, is not equal to A and B. And you can see the shape is like a debe, and the angles alpha, beta, and gamma are all equal to 90 degrees, just like for the cubic. The difference between the cubic and the tetragonal is just in the size of the unit vectors A, B, and C. So the body-centered tetragonal, the difference between this and this is there is an atom sitting at the center. Here, all the atoms are sitting in the corners of the. Need to look for more of these structures, and I say they are available if you want. They are all available if you want. Now we can, let me see whether I can show you others here. Do we have? Now we may not have. Yes, they are here. The cubic, tetragonal, and orthorhombic, monoclinic. We have hexagonal, triclinic, rhombohedral. So there are those different, and you can see them if you wish. You can look for them to see the others. So for purpose of this class, we only showed two. And then we talked about Miller indices, which we said is a convention for describing planes in a crystal. And we use these parameters H, K, and L, and we give the steps how we obtain the Miller indices. Number one, we find the intercepts, we take reciprocal, we'll take LCM, and then we arrive at what we call the Miller indices. An example is given here. Look at this. I want to ask the class rep if he's listening to me. Class rep, can you read example 2.1?
Determine Miller indices of the plane.
Okay, good. You can see the plane. The dotted line is indicating this line. So the plane is like lying on the z-axis, but touching also the y-axis and the x-axis. So you should see, I hope each one of you can see in 3 dimension, and we have indicated, we have tried to scale the axis so that this is one unit, another unit. So we can say this plane is intersecting the y-axis at 2 units. You can see I put 2 there. It is intersecting the x at 1, 2, 3 at 3 units, then z at 1. So we can say the intercepts. We list the intercepts on the x-axis. The intercept is 3. On the y-axis, the intercept is 2. On the z-axis, the intercept is 1. Now, if I take the reciprocal of 3. It becomes 1 over 3. The reciprocal of 2 is 1 over 2. The reciprocal of 1 is 1 divided by 1. Now, these are not Miller indices, so I need to take the LCM. And the LCM, I want to get the LCM of 3, 2, and 1. Anybody who can tell me what is the LCM of 3, 2, and 1? Anybody who can say it? If your hand is up, you can just say it.
6.
It is? Okay, good. The LCM is 6. So I will multiply each one of the reciprocals with the LCM. 1 over 3 multiplied by 6 is 2. 1 over 2 multiplied by 6 is 3. 1 over 1 multiplied by 6 is 6. So the Miller indices are 2, 3, 6. We don't read as 236, we read as 2, 3, 6. And we don't separate with commas. That is the convention. But you can see the reciprocals are separated with commas just for clarity. So this is an example of a plane sitting on the X, Y, Z planes. We can see another example. Who can read example 2.2? Any volunteer? Okay, please go ahead. The person who has raised up their hand.
Determine the Miller indices of a plane which is parallel to x-axis and cuts intercepts of 2.5 respectively along y and z axis.
Okay, read again, please. Please repeat.
Determine the Miller indices of a plane which is parallel to x-axis and cuts intercepts of 2.5 respectively along the y and z axis.
Okay, good. So now this problem, you are not given, the plane has not been drawn for you. In example 2.1, the plane was drawn. But in example 2.2, the plane has not been drawn. You are only supposed to visualize and see, we are taught it is parallel. Therefore, it is not intersecting the x-axis, but it has intercepts on the y-axis, an intercept of 2 on the z-axis, an intercept of 0.5. Now, if we want, we could visualize. We are taught it is parallel to the x-axis. So how is it sitting? It will never intersect this. So it is like it is intersecting somewhere here and here. So how is it? How is a plane? Visualize that plane which only intersects the y and x axis, sorry, z axis, but not. Therefore, that plane is parallel to the x axis, as you see here. So where is, if a plane is parallel to this axis, where will it intersect the axis? Will it ever intersect? If it can intersect, we visualize it doing it very, very far, which we call in mathematics infinity. So a parallel plane will intersect that particular axis at infinity. That is why when we are listing the intercepts for this particular question, that will give on the x-axis, the intercept is infinity. The intercept at the y-axis is 2b. What is b? b is the unit vector. The intercept at the z-axis is a half. And why we are putting c? Because we know c is the unit vector. Therefore, we go to step number 2, which was not listed among the steps, where we divide by the unit vector. And which are the unit vector for x-axis? It is A. For y-axis, it is B. For z-axis, it is C. So I take infinity divided by A. What do we get? Infinity divided by A. Infinity is a very large number, so when you divide it by any other number, it just remains as infinity. So what is this A? Is the unit vector. 2b divided by the unit vector b, we get 2. Half divided by the unit vector c, we get half. So actually this step we could have skipped it and just go straight to the saying the intercepts are infinity, 2 and a half. So I could have gone straight without putting in the unit vectors, but we'll see somewhere in another example where it is important to do that. So I take the reciprocal of infinity. The student who read this example, what is the reciprocal of infinity?
1 over infinity.
The reciprocal of 2?
1 over 2.
Reciprocal of half?
2.
How do you get 2? How do you get 2? Okay, when we want the reciprocal of half, we'll just say 1 over half. 1 divided by a half. And that will be 1 over 1 times 2 over 1, which gives us 2. So then we will need to take the LCM of the student who read this example. What LCM do we need to take? LCM of what? Can you tell me? LCM of what?
Infinity, 2 and 1.
Of infinity, 2 and 1. So what is the LCM of those? Actually, this one we just forget about it because 1 divided by infinity is 0. 1 divided by infinity is 0. So we only take the LCM of 2 and 1, which is, what is the LCM of 2 and 1?
2.
It is 2. So I'll multiply half by 2 and get 1. 2 by 2 I get 4. And that gives me the Miller indices 0, 1, 4. 0, 1, 4. I hope each one of us is able to appreciate how we have done this question. Without having a diagram, we just visualize and imagine how the plane is sitting. Then for homework, we could have given more examples, but I think that is left to you. Look at this homework. Define lattice. What is lattice? Define the primitive cell. Define unit cell. I think yesterday we defined unit cell. Now, question number 2 for the homework: a plane parallel to one of the coordinates has an intercept of infinity. Is the answer true or is it false? We just add a question here involving infinity. Then question number 3. So I want you to take a snapshot of this homework. Please take a snapshot so that you do at your own time the homework. So question number three, the Miller indices of a plane parallel to the y and z axis, what are they? If it is parallel to y and z, it means it cuts across the x-axis. Now, question number 4, determine the Miller indices of a plane that makes intercepts at 4a with a small dot at the top. Anybody who can tell me what this is? This A with a small dot at the top, what is that? Anybody who can tell me? That symbol A with a small dot on top, what do we call it? So anyway, this we call it angstrom, and angstrom is related to the meter. Maybe you can find out how is angstrom related to the meter, the unit we know for measuring distance. So this question determines the Miller indices of a plane that makes intercepts at 4 angstrom, 3 angstrom, and 8 angstrom on the coordinate axis of an orthorhombic lattice with the ratio of the axial. Now this question is very interesting and I want each one of you to do it. Now you can even see we are given the ratio of the axial length as A to B to C as 2, 3, 1. 2 to 3 to 1. So please do these questions. If you have taken a snapshots, we could move to something else. So we understand what crystal structure is. We understand how to get Miller indices of the planes in a crystal, how the atoms sit in the crystal, which is described by the Miller indices. So that is what we were supposed to discuss in that set of slides. We still have time, we can look at something else. Now, those who may have forgotten my name, it's there. Office, I said, you can find me in this office between 7 to 8. After that, I think the class rep knows where else you can get me. This is my cell number if you need to call. And if you need to write using email, this is my email address. There's a dot between the two names at ku.ac.ke. Okay, so well, let's imagine when we have very many atoms in a solid, how are the atoms arranged? Initially, we had looked at a single atom and we were able to get the electronic configuration. We could tell how many electrons are sitting in 2s, how many are sitting in 2p, and so forth for a single atom. But in a solid, we have very many atoms, such that we can form what we call energy bands. Let me just see this. Did somebody raise up their hand? I had a thinking on. Okay. So let's try and see whether we are able to differentiate between a single atom structure and many atoms structure. So that one, we use what we call a band model to be able to explain the structure in solids, the structure of or the electronic configuration in solids. The electronic configuration in solids, we said for a single atom, we can easily get the electronic configuration. But in solids, where there are millions of atoms, we talk of energy bands. So we talk of a band which we call conduction band. We talk of a band which we call valency band. So we have those two bands, and there is a gap between them, which we'll say what we call them. So if we take all the electrons in the valence band for each atom, we form what we call the valence band, which is composed of very, very many bands. Now, if we take what we call the conduction band, is where electrons which can conduct are sitting. So again, we have those many bands and we can form them. And this conduction band, we also call it the lowest nearly empty band. And above the conduction band, we have many levels which are empty, and we can call them empty upper bands. The same thing is happening here around the valence band. We have the valence band also known as IST, nearly filled band, or it could be fully filled. Remember, the valence band can be completely filled or partially filled, as we saw when we were looking at the electronic configuration. And then below the valency band, we have all the energy levels filled. Again, when we are taking the electronic configuration, if I may just show it, I think you remember how we were doing that. And we were able to show that when the second shell is filled, electrons go to shell number 3. When shell number 3 is filled, they go to shell number 4. So for solids, we talk of energy bands. So the distance between the conduction band and the valence band, there's a name we give it. We call it the energy gap. Let me show you here. Look at this. Conduction band and valency. That distance, we can call it energy gap or forbidden. And when we say forbidden, we mean in this energy gap, we don't allow any energy states to be formed here. That's the reason we call it energy gap. Okay, I was looking for a better diagram, but I think that's that. So the distance between the bottom of the conduction band and the top of the valence band is what we call the energy gap or forbidden gap. Now we shall see the importance of the energy gap. When it is small and when it is large, what is the difference? Anybody with a question that far? If you have a question, if there's something you have not understood, you can ask. Yes, please ask. If it is hand which has been raised up, someone can speak and say the question. Okay, so silence tells me there is no. Yes, somebody speaking?
Can you repeat the reason why it is called an energy gap?
Okay. The reason the distance between the valency band, the top of the valency band, and the bottom of the conduction band is asking. We repeat and explain why we call it energy gap. Now, this level, the energy band we call valency band is, if you remember Bohr's model of an atom, where the shells are at different levels. And there is that shell which we are calling the valency band, the outermost shell, which is either fully filled or partially filled. Above it, if we want electrons to conduct, they must leave the valency band. They cannot conduct when they are in the valency band. So sometimes they get a small amount of energy. That energy could be coming from it. When temperature is higher than 0 Kelvin, we have some electrons being promoted from the valency band to the conduction band. And there is energy which is required to do that. So the energy difference between the valency band and the conduction band, we call it energy gap. I don't know whether I've explained it in a way that student can understand.
Yes, thank you.
Okay. So if we look at these points which say that an electron in a totally filled band cannot take part in conduction because it doesn't move. We are going to explain very, very soon how we get, when an electron moves, what does it leave behind? When it's very simple, like if you are in your room and you leave your room, what have you left behind? If you are sitting in your room, then you leave, you lock your door and go away, what have you left in your room? Somebody say? If your hand is up, you can say it. You are in your room, then you leave.
Space.
Yeah, you just leave empty space, okay? Or you say the room is vacant. So a totally empty band cannot contribute to current flow. So you can see these 2 points are extremely important in semiconductor physics, that a fully filled band does not allow electrons to move. Likewise, a fully empty band cannot contribute to electron conduction because it doesn't have electrons in the first place. So when we have an electron, let me take you back to this diagram. If an electron leaves the valence band and goes to the conduction band, it leaves behind a vacancy or empty space, as somebody put it, if we are looking at a room. So in electronics, we say if an electron moves, it leaves behind a vacancy, and that vacancy, as a name given, is known as hole. So we have an electron moving from the valence band, it leaves behind a hole in the valence band, and an electron sits in the conduction band. I don't know whether that is clear. The movement of an electron creates a hole. So we expect to find ores in the valence band and electrons in the conduction band. Because normally it is the valence band is the topmost shell which is filled with or partially filled with electrons. And those electrons, if they get a small amount of energy, maybe from each, which we call thermal energy, they migrate to the conduction band and they leave behind a vacancy, and that vacancy is known as all. You can see here, and all behaves like a positive charge carrier. An electron behaves like a negative charge carrier. So we are building on something which we want to do later when we are talking about conduction in semiconductors, carriers. So an electron or a hole, we call them carriers. So please take note of that terminology, which we'll use later. I think we have said all this. Okay. Now look at this. I think we looked at this diagram. It's just showing us the energy gap or the forbidden gap. That gap between the valency and the conduction band. So when we show like this, we call this diagram an energy band diagram. Which bands are shown here? The valency band and the conduction band. And we measure the energy between them either using joules or another unit for energy we call electron volt. Maybe in secondary school, when you are looking at photoelectric effect, you may have heard of this unit of energy we call electron volt. And we can simply define an electron volt as 1.6 times 10 raised to power negative 19 joules. That is what one electron volt is. So you can easily change from electron volt to joules or from joules to electron volts. So 1 electron volt equals to 1.6 times 10 raised to power negative 19 joules. So it's a unit we'll be using when we are talking about energy in, especially at the atomic level. So having mentioned that, now we can go to something slightly different, but still concerning energy bands, what we call Fermi level, Fermi energy, and the fermi-dirac distribution function. So here we are going to look at three things. What is Fermi energy? What is Fermi level? And the third one is, what is the fermi-dirac distribution function? What is the fermi-dirac distribution function? So Fermi energy is defined as the highest occupied energy level of a material at 0 degree Kelvin. Now, can you be asked to do that? Yes, you can be asked to define Fermi energy. You can be asked to define Fermi level. So Fermi energy is defined as the highest occupied energy level of a material at 0 Kelvin. And then we also note that all electrons in a body occupy energy states at or below the body's Fermi energy. So are we able to differentiate between Fermi energy and Fermi level? So Fermi level is defined for any temperature. We can only define Fermi energy at 0 Kelvin. So we can say Fermi level is the total energy level including kinetic energy and potential energy. But Fermi energy, we can only define it at absolute 0. Look at it here, the definition. So you will find yourself confused between those two terms, Fermi energy and Fermi level, because even in usage, we tend to use them interchangeably to mean the same thing. But at least we have attempted to show they are different. So the third thing we want to look at is the fermi-dirac distribution function. And here you are going to see something you have never seen in your secondary school education. This one, this equation, is the one we call the fermi-dirac distribution function. But before we do that, before we look at this function, we need to look at how we indicate the Fermi level in energy diagrams. Is anybody asking a question? Now, if you want to ask a question, you just raise up your hand. I can pick out. Okay, Wangui, I see your hand up. Please say your question.
Okay, sir. There is something that I didn't get well. I would like some clarification between Fermi energy and Fermi level.
Mumbi, Musioka Mumbi, I think your hand was up also. Say your question. Brian, your hand, I've seen your hand up. Ask your question when you raise up your hand. Anyway, so let's see once more how to explain the difference between energy, Fermi energy and Fermi level. So the definition of energy, Fermi energy, is the highest occupied energy level of a material at 0. So the definition of Fermi energy must be connected to the temperature, and it is only defined at 0 Kelvin. But Fermi level can be defined at any other energy. Sorry, at any other temperature, the Fermi level. So when we say that we can define it at any temperature, then we can say it is, what is this Fermi level? It is the total energy level including kinetic energy and potential energy. Okay. So I don't know whether it's a bit better for that student who asked.
Yeah, it is okay. Thank you.
Okay. So this is the way we indicate the Fermi level in different materials. For a metal, we know metals are good conductors of electricity. So there is an overlap between the conduction band and the valence band. And the Fermi level is somewhere in between that overlap. Now, for a semiconductor, there is a smaller gap. There is no overlap between the conduction band and the valence band. And the Fermi level, which is imagined to be, it runs across the middle of the energy gap. And you can see the energy gap is quite small for a semiconductor as compared to that of an insulator. The energy gap is quite large. So here you can be asked to compare the energy gap for semiconductor and insulator. You just say the energy gap for a semiconductor is smaller than the energy gap or the band gap for an insulator. And again, now the Fermi level is in the middle of the energy gap for both insulator and semiconductor. It's only the size of the energy gap which is different for those two materials. So let's briefly look at the fermi-dirac distribution function. I think you are students in mathematics, and somewhere you will do probability. So this function is actually a function for determining probability. What probability does it determine? The probability that an available state at energy E is occupied. So f of E is the probability. And how do we determine the probability? We use this equation, which gives us 1 divided by 1 plus E. This E, we call it exponent. E raised to power E minus F, EF, E minus EF divided by KT. So we have said E is exponent, and I think exponent is there in your calculators, so you can calculate. So what is E? E is the energy where we want to determine the probability of an electron being there. EF is the Fermi level. K is what we call Boltzmann constant. T is absolute temperature, and it must be in Kelvin, the absolute temperature. So this K has two values. I said maybe this function, almost all of you have never seen it, or there has not been a need for you to know it. Now there's need. So the value of K, which we are calling Boltzmann constant, is 1.38 times 10 raised to power negative 23 joule per Kelvin. Now it has another value, which is 8.617 times 10 raised to power negative 5 electron volt per Kelvin. So whatever you do with them, they will give you the same results, whether you use Boltzmann constant of this value or Boltzmann constant of this value. So let's see an example. Can one of you read example 3.1? Any one of you read example 3.1? Any volunteer?
For example,
Yes. Go ahead, please. Yes. Read.
for a sample at a temperature of 800 kelvins, what is the probability that a quantum state whose energy is A 0.10 eV above, B 0.10 eV below? The Fermi energy will.
Okay, sorry. And before you continue, please, You are saying EV. What do we say EV means? Anybody who can remind us?
Electron volts.
Yes, electron volts. An electron volt is a unit of energy, and especially in at that atomic level, we use very, very small energy. So this energy we are given, as that student has read, we are given that sample is at temperature 800 Kelvin. And the question is, what is the probability that a quantum state within that sample, if it has energy 0.10 electron volt above or 0.10 electron volt below the Fermi energy? So if I can use a diagram, if you see here, it's like we are saying, okay, that quantum state, there are two states we are considering, one above the Fermi level, one below the Fermi level. So we ask, what is the probability it will be occupied? Yes, somebody is asking a question. Okay, so if there is no question, we can look at, we are given these values. So we look at the fermi-dirac distribution function and we ask ourselves, are we given, what are we given? First, we are given the energy difference between the Fermi level and the level where we want to determine the probability. And that is given by the difference between E and EF. So in this, we can do this. We can now simplify this fermi-dirac distribution function by first we determine the power of E. And the power of E is E minus EF divided by KT. So are we given EF? Yes, this one above, it is 0.10. KT, do we know the value of K? Yes, we were given them here and we can use them. So if I want to use, if I'm using electron volts, then I will use this value of the Boltzmann constant. If I want to work in joules, then I'll use this value of the Fermi or the Boltzmann constant. So here we are, we substitute for the energy level difference is 0.10, K is 8.62 times 10 raised to power negative 5 electron volt per coulomb. Oh, sorry, per Kelvin, multiplied by the temperature, which is 800 Kelvin. So you can see this Kelvin and this one will cancel out. This electron volt and this will cancel out. So if you work out what that arithmetic gives us, you find it gives us 1.45. So the 1.45 is the power of E. So you go to your calculator and you take 1 divided by 1 plus E raised to power 1.45. If you find it difficult, you can just first of all work out the E raised to power this. So if you are careful, you'll find it is 0.15. So we are saying when we get this 0.19, we are saying it is the probability. The question was, what is the probability of a quantum state whose energy is this being occupied? So the probability of a function of a level, this level, which we have labeled here as EA, of an electron being in this level, it is 0.19. Then we want to determine the probability of an energy state below the Fermi level being occupied by an electron. We repeat the same thing, but now our difference, we know that EF will be greater than EB. So when we subtract E minus EF, it will give us a negative. So now our power of E will be negative 1.45 because the values are the same. The energy difference is 0.10, but it will be negative. We divide by the same value of Boltzmann constant and the temperature. So it ends us giving us a negative number, and we put it in the fermi-dirac distribution function, which is 1 divided by 1 plus e raised to negative 1.45 to give us 0.81. Therefore, these two answers are telling us there is more likelihood for an electron being found in this level than in this level. So is it clear to all of you? Anybody with doubt, you can voice it. Okay, so if we have understood that, maybe we can do this homework. Please take a snapshot of this homework and do it. Now you have 2 homeworks to do. If somebody is asking a question, please just speak up.
I have a question.
Yes.
You said that the conclusion of the other question is,
Yes.
what did you
What
say
is
the answer? Which level would be occupied? Which Fermi energy?
Okay, we are being asked. Okay, let me ask a question now, which may be easy to make you understand. Now, what is the probability? What's your name? The student who has asked the question.
Esther.
You are Esther. Okay. Now, if I ask this question, the probability of Esther being found in KU today is very high because she has a class. On a Sunday afternoon, the probability of Esther being found in KU may be lower because it's not a day when you have classes. You can go out, you can go home, and so forth. So the same way here for electrons, we are asking, where are we likely to find an electron at this temperature? Is it at a level which is above the Fermi level or at a level which is below the Fermi level? And we have calculated the probabilities. For the first case, we find the probability is 0.19. For the second case, the probability is 0.81. And please confuse yourself, you are able to do this. So the probability here is 0.19, 0.81 for this one. Therefore, it is more likely to find an electron in this system being in this level. Just like I gave that example of Esther being likely to be in KU on a school day. On a non-school day, she is not likely to be in KU. So there's a larger probability. Esther, you understand?
Yes, I do. Thank you.
Okay. So please, each one of you, please look at this homework. If you know how to take snapshot, you can take a snapshot using your computer or your phone. At least I think you know how to do it. So now you have 2 homeworks. The one we gave for when we had class yesterday and today. So we will stop at this point. If you have no question, you can sign out. Remember, I'll get the attendance register generated by the system. Okay, so enjoy your afternoon. You may sign out of the class.
Copy.
Yes, a question. If you have a question, you can still ask.
No question.
Yes.
Can you share the notes?
I share the slide, okay?
Yeah.
Yeah, there you are. What was the question? Is it a question from this slide or another one or this one?
That one.
Ask your question.
For the
Give me,
part
sir.
B, why is the exponent becoming negative?
Yes, because we are subtracting. Look at this small diagram on the side here. For when we take the difference between E and EF. Now, for this case, because the level is below this one, EB has a lower energy. So when I say EB minus EF, it is a small number minus a large number. Did you get negative?
Yes, you do.
Yes. So that's how we are getting the negative.
Okay, thanks.
Okay. Any other question? Okay. Enjoy your afternoon then. Felix Mola, you have a question?
Excuse me, sir. Can you share the slides
I share. What do you mean share?
with the class representative?
Why should I do that? Do you have a good reason why I should do that? Felix.
Yeah, I want to use them for some research of the same questions.